So hello everyone. um, I'll just switch my screen. Okay, that it would be better right now, and I'll pop out the chat. Okay, we have already opened tab here, right? uh, okay, so today we would be doing so today we would be doing okay, my voice is audible, right? So today we will be doing the next chapter, which is parsing expressions. I did some code for the chapter 5th offline. So I'll I'll take you through what I've written. So this is mostly taken from some other implementation of the visitor pattern that I found on GitHub, and it is quite easy to understand because I came to know that the function paradigms doesn't really work well with the rest thing, right? Because it is a mixture of functional and some object-oriented programming. So we did it. So what this is, we defined a enum for expr. This would contain all the four things: binary, grouping, literal, and unity, and these all the things which consist inside every aspect of it. And for the visitor, we defined a generic trait to visit all the functions and return the type that which would be implemented on. For example, we implement visitor for string with AST printer. This is to just print all the ASTs that we form, right? So internally this would, based on the expr, this not the expr, but this, okay, this just calls the specific function for the parenthesis for all the visitors, right? It is not specific to anyone. And what differentiate here is something here, right? This is the main method which would be called from an outside. This is generic over R, and it would what it would do is it would specifically call the designated function for each of the aspects of expr, right? So based on the visitor, right? If the visitor uh, is of binary, which in that case self would be also of expr binary, right? Then this visitor would just call the visit binary expr. So I guess this is it. Actually, it is not based on the visitor, it is based on the self parameter, which is generic over R. And according to this self, we would be classifying all the methods that we need to call. For example, this is the common one, right? This you could say object. This is the entry point of all the generic functions that we can write up based on the R here. So yep, I guess this is it. And we also wrote a test here, which this is just an expression, right? Then we make a instance of AST printer, and printer.print would call this, and this was internally called with except function, which I just showed you. And what it would do is, based on the self parameter here, which would be passed from here, right? And this is a type of expr, and expr of binary, right? So based on the expr binary, this would be called, right? And this would internally call visit binary expr, which is implemented here for visitor string. it is a bit confusing if you first look at it. It was for me also, but in the end it is not that complicated. I guess we need to just uh, learn something new every day, right? Okay, check funnel. This should be, we should be checking this in the future, right? Okay, so moving on with the next. Is anyone watching right now? No, I guess no, no one's watching. uh, I would make a video. I would also like to make a video on these topics, right? I guess most people are not watching because my channel is new and I have low subscribers on it, right? So it would be better to make a video out of it. Yep. So this is parsing expressions. I guess there we would be. Uh, let's just see now what we would be doing with the hair. I don't have any idea because I haven't read this chapter yet. So let's see. Also, we need to take care of the has errors attribute, right? That we made. That we didn't make right now because I didn't knew how to incorporate that with the Rust code. So we need to take care of this in the future. Hmm. Also, if you are new, you can follow me on Twitter and GitHub if you like my content. Yup, that's it. I guess it's in my bio also. Okay, let's just start with this. Remarks the first major milestone in the book. Many voices go together, which measure able to express the substring operations to start some Okay, this is something to take care, I guess. uh so here, if you read it, in the last chapter I said you can play a context-free grammar like a game to generate strings. Parser play a reverse game. Parser plays a game in a reverse. Given string, a series of tokens. We map those tokens to the terminals in the grammar to figure out which rules could have generated that string. Okay, this could have part. The could have part is interesting. It's generally possible to create grammar that is ambiguous. What is meant by ambiguous? Open to more than one, not having one obvious meaning. Okay, not clear, decided. Okay, unambiguous is clear and ambiguous is not so clear. When parsing ambiguity means that parser may understand the user's code as we parse. We just are determining if the string is valid logs code. We are also tracking which rules match which part of it so that we know what part of the language each token belongs to. The expression grammar we put together in the last chapter. We're starting with the expression binary. Okay, this would be binary. Then this would be unary. For the left hand, there's pick the numbers and use 6. Okay, for the right operator pick, and for the right hand expression pick binary again. Okay, in the nested binary expression pick 3 minus 1. Okay, that is good. Okay, so we start from the middle. If I can pick it up, right? And then starting in this expression pick binary 6 by 3. For the left hand expression pick binary again. Okay, for the right hand we can just use minus 1. Pick number and use minus 1. Okay. Okay, this is interesting, right? 6 by this is the first one, right? We starting with the resolution pick number 6. Okay, then this, and this would be another binary, which on the left would 3 would give 3 for the operator minus, and for the right 1. And this is for the second one, right? Starting expression pick binary. Okay, for the left hand pick binary, and for the right one pick a number. 6 by 3 minus 1 or 6 by 3. Next, which way you want. A parser would be a recursive one, right? Which would follow up post order traversal, like we see in the, like we saw in the previous chapters. So according to the post order, what let's see what it would give, what the first one and second one would give. So let's see docs.new, and okay, so post order is left, right, and then the node, right? So it would go left, which would give 6. 6. Okay, okay, 6, right? Okay, then we go on to go to the minus, then we go to the 3. This would be then give 3 3 3 1 minus 3 1 minus. This would be in a group. And this was whole be returned, and 6 this group and divide 6 this group and divide. This would be the first, right? Given by first case, and for the second this would give 6 3 divide 6 3 divide 6 3 divide and 63 divide, then 1 and then minus 63 divide then 1. Okay, here you'll also a number and an expression, a number and expression. This would give us a number, right? For example, 6 by 3. Let's see what is right and wrong. Term can have plus 2, but it also 3 star 4 by 5 values. So associativity determines this is okay precedence which would be given higher priority, which operator would be given higher priority than the other one. This is precedence. This is okay. I'm a bit confused in this. What is left associative and right? Left to right when or what is related first in the series of same operator? Oh, okay. This is also okay. So if this is negative minus left minus is left associative, so it would be 5 minus 3, then whatever the answer is, then 5 minus 3 is 2, right? Then 2 minus 1 would be okay, and 7 is right associative, so b equals to c, then a equals to b equals to okay. This makes sense without we'll define precedence associativity and expression that uses multiple operators is ambiguous. Right. Can be passed into different syntax tree, which could be turned evaluate to different results that while supplying the same precedence rule. Okay. Comparison, term, factor, unity. Right now the grammar stuffs all expression types into a single expression rule. That rule is used as a non-terminal for operands. Expression equality. Equality is this, I guess. Okay, this is equality. Comparison is this. Term, factor, unary, primary. Term, factor, unary. What is primary and expression would be the one which have binary or any other operators. What is primary? I need to see what is primary. Each rules here only expressions match expression at the precedence level or higher. For example, unary matches a term unary like negated. Okay, or a primary expression like okay. So the lowest is equality. So this is in reverse order. I was thinking that these are from higher to lower. This is lower to higher. So this makes sense because if you read it, each rule here only expression represents level higher. For example, unary. So it would match the rules for unary and could match your rules for primary also, which is written here exactly the same. Primary is 1 2 3 4. Okay, I need to say this. What is primary? Okay, so here it is covered. Okay, we'll go from here. Expression gives equality and expressions give equality. So let's just see. Since equality has the lowest present, if we match that, then it covers everything. Expression gives quality. Why? Over the Okay. Factor would gives primary or unary. Gives unary, which in turn would give primary, right? The remaining rules are for binary operators. Factor with factor slash star unary. Factor gives factor, then divide or multiply unary. Unary would give not or minus unary or primary. So not 1 2 3 4 divide this. This makes sense. Okay, the rules the left operand. The rules regard this to match the left operand. Putting the recursive production on the left side and on the right side makes the rule left associative and unambiguous. Okay, yeah, sure. Recursive is on the left because factor would give factor, and unary on the right makes the rule left associated and unambiguous. Unary on the right. Okay, this is okay. All of this is correct, but the fact that the first symbol is in the body of the rule is the same as the head of the rule means this production is left recursive. Okay, some parsing techniques, including the one we are going to use, have trouble with left recursion. What? I thought left recursion was okay to do. Okay, so right recursion wouldn't. Okay, okay, yeah. I guess in the course that we took in our CS degree, there was something called theory of computation, right? Where I guess we need to remove the left recursion in order to generate context-free grammar. I guess this is also the same. I was confused if we need to remove the left recursion or the right one. So we need to remove the left one, I guess.
अबे डूम स्ट्रीम कर रहा है क्या? अरे तो हेलो
So where were we? We were we were at. All is this correct? Okay, we were doing. We were reading about the left recursion, right? We need to remove the left recursion. And in order to do so, some present you have to do with left recursion, so like it's not a problem. Okay, a factor would give a unary and forward slash or star unary, and this star means that this could be repeated 0 or infinite times. So if we see here, factor gives unary. Okay, okay, this is fine. If it doesn't even go for ones, so this would give factor gives unary. Factor gave unary. This would be the second case. And in case if it gives only one time, so unary gives forward slash star unary. Okay, in that case, factor would be replaced by unary, and all of the things would remain same. Okay, we define a factor expression as a flat sequence. Multiplication and division. This matches same syntax as the previous rule, but better mirrors the code we'll try to parse logs. Okay, these are all the things that we just discussed above, right? Factor this. Mm-hmm. Okay, so here we are, I guess. Here we are parsing the expressions, right? So there is different types of parsing. There is a whole pack of parsing techniques whose names are combination of L and R. Left recursive. I have seen some things like this in TOC, right? The theory of computation. LL, LR, LALR, CLR. There was something like CLR also. Along with more exotic beasts like parser combination, early parser, shunting yard algorithm, and backward parsing. I guess I wonder what Rust uses. Let's see. So Rust uses a simple recursive descent parser. This is inside Rust parse. Okay. Okay, so we are at something. We are at something, right? Okay, this is just like what we are using expr. These are for expressions. This is the parser. These are all the tokens. Okay, so this also take previous token into account than the current token. Okay, and this is a parse session. This would I guess contain all the context about this session, this parse session, right? I need to look into it. What this contains also restrictions, token types, token cursor, num calls. Okay, this is somewhat okay, so it is quite a bit lengthy. Okay. TY. I don't know what TY is. Okay, mute visit. Okay, this is tests only. So this is all the things inside the parser. This would be interesting to see. Okay, this for this question I think I do know. So the first version of Rust was written in OCaml. Yeah, OCaml, and then what they did is they did the bootstrapping of the compilers. So what bootstrapping means is, so first version was written in OCaml, then from the OCaml they shifted to, I guess, Rust, and what they did is they used the previous compiler to build upon a new compiler, right? So from then Rust is using its own and I guess this is the part. Yep, here it is. So written in some other language, and then you can use that version to compile the next version and the next and so on. So this is what it is. It is something. There's an old joke that the second Pascal compiler was written in Pascal and compared with the first Pascal compiler, which was a grad student. Okay, this is written in OCaml. This is a this is something clever, right? You can see here recursive descent parsing. So here comes some coding involved. From now on we would be coding. Let's see. Okay, this we have done. For our first number technique, we more than sufficient is recursive descent. And what does this also uses recursive descent, right? The rest one. So I had done recursive descent parser with the variable but small located. Look ahead would be PRSCR. Okay, look ahead would be, this is the previous one. What is a look ahead? Let's see. Doesn't require using complex parser generator tools like YACC, Bison, or Antler. All you need is a straightforward handwritten code. Don't be fooled by its simplicity though, because the distant parser are fast, robust, and can support sophisticated error handling. In fact, GCC V8, the JavaScript VM in Chrome, Rosslyn, the C Sharp compiler done in C Sharp, and many other heavyweight production languages implementation use recursive descent. It rocks. It's considered top-down parser because it starts from the top of our outermost dumb rules. Here, expression. Okay. Let's way down into the nested subsection before touching the leaves of the syntax tree. This is in contrast with the bottom of parsers like LR that starts with primary expression. Okay, a recursive descent parser is a literal translation of grammar's rule straight into an imperative code. Each rule becomes a function. The body of the rule translates to a code roughly like. It's called because it's on the grammar. Confusingly, we also used direction metaphorically when talking about high and low precedence, but the orientation is reversed. In a top-down parser, you reach the lowest precedence expressions first because they may in turn contain some expression of higher precedence. Top grammar and bottom. Unity is the higher precedence, right? And the top down parser, you reach the lowest precedence expression first because subscription because they may in turn contain a expression of higher precedence. Okay. Let's start on the direction of stacks grows or why trees have roots on their top. Okay. Okay, here comes the coding part, right? It turns out we can't make something final here. I know why this is final, because all the tokens list would come from the lecture, right? So this this makes sense if this tokens list is final and we couldn't change it. Okay, like the scan of the parser consumer flat sequence on we are reading tokens instead of characters. We store the list of tokens and use current to point to the next token. Currently waiting to be parsed. We are going to run straight into the expression grammar now and translate each rule of the Java code. The first expression rule simply expands equality rule to the straightforward. Okay. This is expression gives XPR. Let T. This would also be inside. Okay, we wrote the equality. Now this is the thing that we need to write for. I'll just take a look at this equality for once, and then we try to make our own function for the next rest of them. Yup. Exp is a trait, right, which could be a binary enum. Okay. Let's see here. So equality is comparison, then these all things could be generated one or more times. It's not including zero also. Zero or more times. So expression XPR equals comparison. Okay, then while match bang equal or comma equal. Okay, we need to make match and equality comparison function, right? I think I'll just take some time off, like 5 to 7 minutes, and then I'll get back to it. So just hang on this for a second. Right, I'll be back. I'll put some good music. Okay, I'm back. Am I audible? I would be audible. I guess so. So, let's start from where we left off. You're making all this function to parse, right? So we'll just do a to do here, right? And we'll just make some other things. Okay, equality is defined here, right? So what we would do is we would let expr equal to compare self dot comparison. We will make this function here, and we would return expr here, and we will do this to do. Okay, then we'll move on. While we have to match a bank self dot match to token type bank token type bank equal or equal equal, right? Equal equal. I have to make this function also. What we would do is make here, which would take, oh, match is a keyword. Okay, match tokens, control C, then we do this here, and we'll just this click right to do here, and this would give a boolean, right? So what is the error saying? Expected is because of return type. Okay, this is okay. So now what we have to do, we have to token operator previous, token operator previous, self dot previous, then this is the equality one, right? Comparison bang equal equal, and then comparison. This is comparison, right? Expr new binary operator, expr operator, right? This is expr, then this is operator, and this is comparison, which would be right. Okay, why are we taking that token operator equals to previous? What is the meaning of this? Why do we have to take this? Okay, this is an operator here. Okay, I guess this would match the current token to be equal to bang underscore equal or equal underscore equal. Most probably this is that case only, and if this is true, then we can just extract. For token types, token type in token type in types. Okay, this is okay. I know this, what this syntax refers to. It means that there could be n number of arguments here for types, for token type in types. If check type, then advanced, return true. This is doing the same thing that I talked about. uh, check would be here, peak dot type. Then okay, there are a lot of functions that we need to make, but I guess this is only for the one time that we have to make it. Then rest we can just reuse the same functions. This is similar to what we did in while writing an interpreter. What we'll do is just a second, I'll be back. And yep, so let's just code. Here is what we were at. Let so this we got the expr from here. This is called, right? Then we would take the operator. Let operator equal to cell dot current. Operator would be equal to cell dot current previous. This would be self dot previous, and I would need to make another function here. This would be and self, and this would return a token. It would return a token, I guess. TODO. Okay. Then we got an XPR, then an operator. Then we need this comparison. Okay, comparison. Okay. Okay. Also, this returns a token, right? So this is okay. And let this would return a comparison is an expr, right? This could be an expr. expr equals self dot comparison, and we okay, so what is this? And we would let mute, and then expr. This could be renamed expr underscore temp. expr equals expr binary. Left would be expr only, then operator, then the right operator, and expr underscore temp. Then we need to return okay, let's see if we can mimic the arguments here, right? So I don't know why my screen is flickering. This shouldn't happen. There is some kind of a problem with my OS. I am damn sure, because this is just, I don't know, man. I'll just switch to Ubuntu on some time, or Fedora. I'll try Fedora. Are just giving me so much trouble lately. Okay, so we were here, right? So can we? I'll just ask ChatGPT. Can we do something like this in Rust? Token type A, B, C. Token type, token type, 10 types. What are we doing here? Just see. This checks to see if the current token has any. Till here, I am I'm able to gather what this function is doing, but after this, the star loop matches in the rule map to we need to know when to exit that loop. We can see that inside the rule we must first find either a not equals or double equal tokens with the door. Okay. Okay, okay. I got it. So we can. It is better to use. Why is this giving these sort of errors here? Box new, then just do this. This is match tokens, right? We can just use something like array of tokens. Then what we will do, we will do something like this. Okay, let's see what is the problem now. Is my program compiling now? Okay, compiles successfully, but there is some sort of okay, we can just remove this. Right, then we can just move on with the stuff. What box does is it basically allocates some this memory to the heap, right? And by default all the str operations, and by default all the memory, I guess in the rest, unless specified, uh, is stored on stack, right? So box allocates the expr memory onto the heap one, and this is just it. uh, so the error here is, basically this is a recursive thing, right? If we just calling expr, then expr binary, then inside the binary there is also a expr, this would in turn call the expr binary, and the list would go on, right? So in rest, in java, by default the all the things get stored on the heap and on the stack. um, there are variables that points to the heap, but in rest it is different. All this memory, as per my knowledge, all this memory gets stored on the stack unless you specified it. So if it is recursively calling the stack memory, there would be an error of stack overflow, right? So we just allocate this memory to the heap by specifying the box operator here. Box, not enum, but box struct box. And this is, you can read it here, it uniquely owns a heap allocation of type T. Module level documentation, you can, I'll see it when we are done with this, and we would head on to the rest compiler. So we were at match tokens. If now, what we need to peek the mm, I'm wondering where we writing all these methods once again, like the check, the previous, the peak is at end. All these are already implemented in the Lexer library, right? So why are we doing this here? There's some kind of a problem with my OS. I'll just restart the stream, right? I'll just restart it. That would be better, I guess. Okay, thanks for watching.